Okay, so welcome back to this next video in which we are discussing an example of calculating conditional expectation. Now we've done our simple example, let's move on to this more difficult example, or slightly more subtle example, which is the expected value of the random variable x given that we know what the value of y is. So I'll just get another piece of paper. Right, okay, so let's just redraw out what we have, which is that we have a abstract probability space here. So this is our abstract probability space here, right? So we have outcomes in here. Then what we had is we had a random variable x, which was mapping you onto the real line. And that random variable x was normally distributed, and it had mean 0 and variance 1, so it was standard normally distributed. Okay. Then what we had is we had another random variable here, which was y, and this mapped you onto the non-negative real numbers, so from 0 to infinity. And basically, the way we had defined this random variable x was we had defined it as a function of our random variable, the way we had defined this random variable y was that we defined it as a function of this random variable x. So we defined it as being x squared. So you took whatever value the random variable x mapped you onto, and you squared that to get the value that this random variable y was going to map you onto. Okay, right. And now what we want to do is calculate the expected value of the random variable x given y. And remember, we're going to think of this in the end as being a random variable, but in essence it's got nothing, it's no different from saying, okay, we're going to look at the expected value of x given that y is equal to, let's say, some little value a. So, remember, y can only take on non-negative real numbers, so a now is restricted. It has to be a non-negative real number, so a is an element of the non-negative real numbers. Right, okay, so let's try and calculate this, and then we'll see how we can set it up as a random variable. Right, okay, so what does this mean? This means, restrict your attention now down to the probability space, which is that y is equal to a. So basically, somewhere in here will be our non-negative real number a. So basically, what I'm going to do is I'm going to cut off all the rest of the probability space and just look at that little section which contains a. Okay, right. Now, what we need to think about is what is the equivalent bit back here which corresponds to that. What's the pre-image of this point A in the abstract probability space? I.e., we want to know what is the inverse, the inverse image or the pre-image of this point A. So this consists of all points which are then mapped onto A by the random variable y. But what are the points that are mapped onto the random variable a? Mapped onto the non-negative real number a by this random variable y? Well, y is equal to x squared. So if we just draw out the graph of x squared. Okay, so here is the graph of x squared. Then if we look at some non-negative real number a, then there are two real numbers that are mapped onto a by this function x squared. There is the square root of a here, square root of a, and there is the negative of the square root of a over here. So there are two numbers in this probability space here which were mapped onto a by this function. So if we look at this, the equivalent probability space in this x probability space here, which corresponds to this probability space just containing a over here, then it contains the square root of a and the negative of the square root of a. Right, so there's the equivalent bit that we're looking at in the x probability space. So now if we go back to this pre-image of a under y, what that is all outcomes here which were mapped onto either the square root of a or the negative of the square root of a by this random variable x, basically. So that's what this consists of. So basically, it is the union of the inverse image under the x function of the square root of a unioned with the inverse image of the negative of the square root of a. So basically take all the points which were mapped onto the square root of a by the function x, that's this bit here, and union that, join it together with all the points which were mapped onto negative the square root of a by this function x. Right, okay, so now what we want to do is we want to look at what is this random variable x restricted down to this probability space. Well, it is mapped, or it consists basically only of two functions. So let's take this out. Well, two numbers. Sorry. Let's take this bit out, because now what we want to do is we've conditioned on this event. So we've conditioned on this pink event, which is the inverse image of this value a. And now what we want to do is look at this random variable x restricted to that, which goes on to this square root of a and the negative of the square root of a. And we want to take the expected value of that random variable. Okay, so here I've pulled this portion of the abstract probability space out, which consists of all outcomes which were mapped onto a by the random variable y. And it is now, you still have this random variable x operating on it, and basically it maps you onto either the square root of a or negative of the square root of a here. Right. Okay, and now what we want to do is we want to take the expected value of that random variable. So this one's slightly more complicated because we've got two outcomes in that probability space rather than one. So how do we take expected values? Well, we times the value by the probability of that value. So what we need to know is what is the probability of this value and what is the probability of this value. Well, now it becomes important that the random variable x was normally distributed with mean 0 and variance 1. Because basically what that meant is that the probability density that you got, the square root of a or negative of the square root of a, was exactly the same because the normal distribution is symmetric, basically. So here is negative of the square root of a, and here is the square root of a. So basically, in the original bigger probability space, the probability density that you got a certain value, or that you got either of these two values, was exactly the same. Now, if we think about how we define conditional probability, then basically it inherits the properties from the bigger one. All you do is you take the probability of each one of these and divide it by the probability of the entire probability space. So it shouldn't change the relative probabilities of these two. Now it's a little bit more complicated than that because we're dealing with probability densities rather than probabilities, so the technicalities are a bit more difficult. What you'd have to do is draw little intervals around each of them and then do it as those intervals approach to 0, basically. But hopefully it should be pretty obvious that if these two had equal probability densities in this larger probability space, then here their probability mass functions are also going to be equal. So the probability mass function that you get the square root of a should be a half, and the probability mass function that you should get negative the square root of a should also be a half. So if we take the expected value of this random variable x, and we're now doing the expected value of it conditional on y is equal to a, which is just the expected value of this random variable with this setup here, then basically it's going to equal the sum over all values that x can take on of that value of x times the probability that that value is equal to little x. And of course we should put maybe there, given that y is equal to a. Okay, right, so the two values are just the square root of a and negative of the square root of a, and the probabilities of each of them is a half, so we get this one times a half plus the other one, which is negative the square root of a, again times a half. Now these just add up to equal 0. So now what we get basically is no matter what little a you give me, the expected value of x, given that y is equal to that value little a, is going to be equal to 0. So it's 0 no matter what the value of a is. So now what we can do is we can view this as being a function. So we're going to view it as being a random variable in its own right, which is going to act on our abstract probability space up here. And it's going to map you onto real values here. And the way it would work is it would say, okay, look at your outcome S, So let's say some abstract outcome here. Look at what value of A it's mapped onto. So look at what value Y maps it onto. Then substitute in here that value of Y. So every outcome is mapped onto a value, a non-negative real number by this random variable Y. Substitute in that value of Y for A here. And then basically calculate this and map your outcome onto that value. Okay, that's what it means to think of this as a random variable. Now, what we've just shown is that no matter what value of A this is, the value of this is always 0. So this random variable is actually going to map every single outcome onto 0, basically, because every outcome is mapped onto some non-negative real number, and for all non-negative real numbers, this value is 0, so all of them are going to be mapped onto 0. So actually this consists of just a single real number, which is 0.